Welcome back, everybody. Let's look at this second example. Because you've done several correlational analyses already, I'm going to let you do this one on your own. I just want to talk about a couple key points. First of all, let's make sure we all understand what we're looking at. It says examine the following data and compute a Pearson's correlation coefficient. Is there evidence that the two variables are related in the population? In other words, is the sample correlation significantly different from zero using a two-tailed test and an alpha of 0.01. So use 0.01 instead of 0.05. It looks like we have data from 2, 4, 5 different people. The two variables are the amount of sleep that the person got the night before, and then the person's exam score the following day. So we'd be using sleep as the predictor variable and exam score as the criterion variable. If we have 2, 4, 5 people that we measured, that means we have 3 degrees of freedom. We can consult our table. We're going to be using an alpha of 0.01. We have 3 degrees of freedom, so we need lots of evidence. The critical values would be a positive and negative 0.959. Go ahead and create a scatter plot. You can see from this, if we were to fit a line through that data, the data points don't conform all that well, really. So this is a much weaker relationship than we had in the first example. I would predict something here like maybe 0.4, 0.5, 0.6. I don't know exactly. I'm just trying to get a basic idea, just a guess. So don't stress about guessing what the estimated R value will be. It's just that we know this isn't, zero, and we know it's not 0.99. When you work through it, if you have any problems, just let me know. But everything is listed right here so you can check your work against mine. Bottom line was we found a correlation coefficient of 0.56, and that's nowhere near enough evidence to reject the null hypothesis. So our results are not statistically significant. So we'd say R with 3 degrees of freedom equals 0.56, P greater than 0.01 based on a two-tailed test. And we were able to account for 31% of the variability. So 31% of the variability that we see in exam scores can be explained by the amount of sleep the student got the night before. Let's take that information that we have right there, and now let's compute a regression analysis. What we're going to do is try to figure out the best fitting line for this data right here. Now we're ready for step 5. We need to compute the slope, which is b in our regression equation, and we also need to compute the y-intercept, which is a in our regression equation. Our regression equation looks like this. We're saying predicted y, in this case, the predicted exam score, is equal to our slope multiplied by the amount of sleep the person gets plus a. I've mentioned before that we should look at our formulas to see what information we have and what information we need, and that'll help us determine where to start. When I look at the formula for the slope, I need to know the sum of the products and the sum of squares for the x variable, the predictor variable. And I know both those pieces of information from the regression analysis we just completed. In order to compute the y-intercept, I need to know the mean of y, the mean of x, which we can compute very easily, and then also the slope, which we don't have yet. So it makes more sense to start by computing the slope. Let's do that. Let's go back a page and let's remind ourselves of what the sum of the products and the sum of squares for the x variable equal. Sum of the products is equal to 42.2, and the sum of squares for the x variable, which is sleep, is equal to 53.2. So that's where these two numbers come from. Let's go ahead and just crunch those numbers real quickly. 42.2 divided by 53.2 equals about 0.79. Now that we have that value, let's look at our equation for the y-intercept. We're going to need to compute the mean of y and the mean of x. We just computed b. So let's flip back to this page and let's go ahead and compute the mean of x and the mean of y real quickly. They both have the same sums, and they both have the same number of people that we measured, so they're both going to have the same mean. Let's compute that mean real quickly. The sum of x was equal to 38. We measured 5 people, so the mean for that variable is 7.6. And as I mentioned, because the sum of y is also 38, the mean of x and the mean of y both equal the same thing. So let's go back. You can see in my equation right here, for the mean of y, I put 7.6, and also for the mean of x, I put 7.6. And there's the value we just computed for the slope. Let's go ahead and crunch that, figure out what the answer is. In our next step, we're going to do this multiplication right here. So we take 0.79 and multiply by 7.6. That equals about 6 if we're going out to 2 decimal places. So we're left here with 7.6 minus 6, so our y-intercept equals 1.6. Now that we know the regression coefficients for the regression equation, we can put it all together. Predicted y, your predicted exam score, equals 0.79 times the amount of sleep you get plus 1.6. Let's play with that equation a little bit. Let's compute some predicted exam scores. We know how much sleep these 5 people got. We know the exam scores for those 5 people. Let's figure out what the regression equation would predict for those people. Let's go ahead and work it out for that first person. So according to our regression equation, we're going to take 0.79 and we're going to multiply that by the amount of sleep that person got the night before, 10 hours. And then we're going to add 1.6. So the regression equation is predicting that this student would score 9.5 on the exam. And we see that this student actually scored 5. Let's check the next one. We'll take 0.79 and multiply by 12 hours sleep. Then we're going to add 1.6. That equals 11.08. So we're predicting the student would score 11.08, and the student actually scored 11. So in this case, the regression equation did very well. Let's just look at another one. Let's take 0.79 and multiply by 3 hours sleep, and then add to that the y-intercept, that constant value, 1.6. That equals 3.97. So we're predicting the student would score 3.97. The student actually scored 0. Before we compute the standard error of the estimate, let's plot our regression line. And remember the way that I like to do it. When I'm looking at my scatter plot, I want to find 2 points that are relatively far away so that I can more easily and more accurately connect those 2 points with a straight line. One thing that I like to use is the y-intercept. The y-intercept is 1.6. So the first point is right there at 1.6 on this y-axis. The y-intercept is where the line crosses this axis, so x must equal 0. In other words, this point is plotted where x equals 0 and y equals 1.6. So there's our first point. Then I like to plot a point that's reasonably far away. We've already computed some values. When we plugged 12 into this regression equation, we found a predicted value of 11.08. So here's 12 on the x-axis, and here's approximately 11.08 on the y-axis. So there's a big dot right there. Now we just connect the dots. That is our regression line. And we can see these points are, close enough to that regression line, but there's quite a bit of variability. The standard error of the estimate is going to measure the variability that we see between these actual data points and these predicted data points. The predicted data points all lie right here on the regression line. Let's go ahead and look at our formulas. Here is the formula for standard error of the estimate. And it consists of various components. We see n in there. That fraction right there is going to be easy enough to compute. We have 2, 4, 5 people, so that's no problem. We need 1 minus r squared. That's no problem either. And another thing that we need to compute right here is s sub y. S, remember, always stands for standard deviation. It's simply the standard deviation for the y variable. Remember, sleep was x, exam score was y. We're going to need the standard deviation of this data right here. And that's no problem. We already have sum of squares. In fact, let's look at that formula for the standard deviation. Remember, the standard deviation is the square root of variance. Variance, go ahead and look at any formula sheet, is simply sum of squares divided by n minus 1. So we're going to find sum of squares. We will compute n minus 1, that's variance, and then we'll take the square root of it. That's our standard deviation. So let's go back a page and find out the sum of squares for that y variable. Sum of squares y equals 107.2. So we're going to stick in 107.2 in the numerator. We'll find n minus 1. We measured 2, 4, 5 people, so n minus 1 is 4. Let's go ahead and crunch those numbers. 107.2 divided by 4 equals about 26.8. And we need the square root of that. So I'll click my square root key, and that equals about 5.18 rounded to 2 decimal places. So of course that's this value right here. So we're going to plug that into our formula. We see it right here. Now let's start working on the values that we need underneath the radical sign. We need 1 minus r squared. Let's remind ourselves of what r squared equals. We computed that right here. It equals 1.31. We need 1 minus that. Let's compute that real quickly. 1 minus 0.31 equals 0.69. So where we needed 1 minus r squared, I put in 0.69 right here. We need to multiply that times this fraction. This fraction is composed of n minus 1 divided by n minus 2. N minus 1 would be, let's see, 2, 4, 5. 5 minus 1 is 4. That's n minus 1. Divided by n minus 2, 5 minus 2, which is 3. So we had 4 divided by 3. That equals 1.33 repeating. We'll just stick with 1.33. So that's this value right here. Now we need to multiply these two things. Eventually we'll take the square root of it, and then we'll multiply by 5.18. Let's first just multiply these two values. So let's take 0.69 and multiply that by 1.33. That equals about 0.9177. We need the square root of that. We could, of course, just hit our square root key. Normally in class, we take things one step at a time and we round things as we go. I'm just going to do it that way, the way we normally do. So we'd be left with about 0.92, and we take the square root. So we would round this to about 0.96. So the last thing that we need to do is take that 5.18 and now multiply by 0.96. 5.18 times 0.96. That equals about 4.97. So that is the standard error of the estimate. That is the standard deviation of these points surrounding this regression line. That's telling us how much the predicted values are right here on this regression line. That's telling us how much the predicted values differ from the actual values on average. Of course, smaller numbers would represent the predicted values doing a better job of coming closer to the actual values. So as I've said before, the standard error of the estimate is a measurement that kind of tells us about the health of our regression equation. It tells us how well, on average, we are predicting values. On the next page of our handout, you see some sample SPSS regression output. Because it's not easy for everybody in our class to run SPSS from their computers at home, we will be doing a regression analysis using Excel. That's for research report number 4. Hang in there, you guys. We're almost done with this semester. There's really only one more statistical test that you need to learn, and that's the chi-square test of independence. And we'll talk about that in the next video. I'll see you then.